What is up, Denell High School? This is Mr. Ayton. This is 8.3 Atomic and Nuclear Physics. This is the last vodcast for our atomic and nuclear, and this is where I'm going to detail a problem. If you remember, if we need our equations, we're just going to go to our equation sheet. And our equation sheet has two different equations. It is waves and it is particles. If you take a look at waves, don't forget that this top equation is for waves or photons, and there's also the C equals wavelength times frequency. If we're taking a look at our particles is going to be our de Broglie wavelength, and don't forget our kinetic energy equals 1/2 mv squared, and don't forget that we can also use our kinetic energy is equal to our potential energy, which is Q times the stopping potential. And this equation right smack dab in the middle is called our photoelectric effect. So let's get to it. Here we have a problem. If you take a look, there's a light of wavelength 400 nanometers, and the light's coming in, and you can see where it says a light, a photon. And so here we're talking about our wavelength coming in is 400 nanometers, and that is a photon of light. And like I said, if you remember, I said make sure you split these bad boys up in your mind of either photons or either our particles. Okay, so here we have photons coming in. That nano means e to the -9 or times 10 to -9. And you can see what happens is the metal surface is absorbing some of that energy and it's kicking off some electrons with a kinetic energy of 1.1 times 10 to -19 joules, and that is a particle because it's kicking off electrons. It's kicking off electrons. So let's try to answer this question. Let's go to A. A says calculate the frequency of the incoming light. You see I circled that word light right there. And why did I circle that word light? It means I'm going to my equations for light or photons. We have C, which is the speed of light. That's 3 times 10 to the 8th meters per second. And that is equal to the wavelength. My wavelength is 400 nanometers. Nano is times 10 to the -9th meters times frequency. Okay? And so all I have to do is divide here. Okay, it's a simple algebra problem, and I end up getting a frequency of 7.5 times 10 to the positive 14. I'm sorry, and the units for frequency is hertz. Okay, because nuclear physics, if you get it, it hurts a little bit. Okay, so frequency is 7.5 times 10 to the 14th. Okay, so I'm going to put that up near A right there. Okay, and I'm going to erase my work so that I can continue going on to letter B. Letter B says calculate the work function. When I see that word work function, that means I'm going to that kinetic energy max equals HF minus the work function. That's the only equation that has work function in it. Okay, what's my kinetic energy max? It's 1.1 times 10 to -19 joules. If you see kinetic energy is in joules, so I have to use the 6.63 number because that is in joules seconds. I have to use units that work. The frequency is 7.5 times 10 to the 14th. I just found that out. And minus the work function. I really highly suggest you doing this math while I'm doing it right here in your calculator. That way you can see whether you know how to do it. All we need is to multiply the H and F and subtract it on the other side. And that gives me a work function of 3.87 times 10 to the -19 joules. Now I can subtract that number, divide that number by 1.6 times 10 to the -19th, and I end up getting 2.42 electron volts. Guys, if you left your answer in joules, this is joules right here, you're totally fine, okay? No problem whatsoever leaving your answer in joules, okay? If you want your answer in electron volts, that's totally fine too. Some of my students, we see that they do different ones, and so I'm just going to put this guy up there. And so that is my electron volts or my joules of my work function. Now I'm going to take a look at my stopping potential. So I'm going to erase my work right there. Okay? And let's take a look at my stopping potential. I'm going to put that in a different color now. And what is that word stopping potential? That means I'm taking my kinetic energy equals my QV, my stopping potential. So what's my kinetic energy? It's still 1.1 times 10 to the -19 joules. Okay? And that is equal to my charge, my Q of my electron is 1.6 times 10 to the -19th coulombs times my voltage. Okay? And so my voltage is called my stopping potential, and I end up getting 0.69 volts. That is my stopping potential. Okay? And so I'm going to put that up there. Let me just erase some of this stuff. And I'll put that voltage up there just to keep my answers straight. Okay. I'm actually going to just take out those little two dots right there, and I'm going to bring this guy up. Now we're on to D. D says calculate the momentum of an electron. Okay, and I'm going to do this in red. You see that word momentum, and you see that electron. What does that mean? I have a particle. Okay, in order to find the momentum, I know momentum equals mass times velocity. I need to find my velocity first. So I'm going to take my kinetic energy is equal to 1/2 mv squared. That's how we find velocity. I know my kinetic energy, it's 1.1 times 10 to the negative 19 joules. Now guys, I have to use the 1.1 number because I can't use electron volts here because joules is the SI unit. I have 1/2 my mass of an electron is 9.11 times 10 to the negative 31st kilograms, and I have v squared, and I end up finding my velocity ends up being about 4.9 times 10 to the 5th meters per second. Now guys, a little note to you. If you end up getting a velocity greater than the speed of light, you know your problem is wrong. You have to be below the speed of light. And now I can just put this in momentum, mass of an electron, times my velocity right there, and of 4.9 times 10 to the 5th, and I just need to multiply. And I end up getting 4.48 or 4.5 times 10 to the negative 25th, and my units are kilograms meters per second. Okay, and that is our first problem for atomic physics. Okay, again, A is a wave problem, C and D are particle problems. Let's go to the second problem. The second problem says that we have allowed energies of a simple hypothetical atom are -6 electron volts, -3 electron volts, and -1 electron volts. And the first thing we want to do is, for A, we want to draw the atom's energy level diagram. Okay, so we have n equals 1, that's my principal quantum number, and that's at -6 electron volts. Okay, and you can see here we have -3 electron volts, that's what we call my n equals 2. We also have n equals 3, and that is -1 electron volt. And if I wanted to show right here of infinity electron volts, that would be 0 electron volts, my bad. 0 electron volts, that would be at the n is equal to infinity. N is equal to infinity. Okay? And I'm going to calculate, B says calculate the wavelengths associated with the possible energy transitions. I can make a transition from here to here. That's from n equals 1 to n equals 2. If you can see, what is the energy from n equals 1 to n equals 2? That took 3 electron volts to jump up there. And what do we know energy is? Energy equals hf. Okay? Now, the h that I'm going to use here is my 4.14 times 10 to the negative 15th. And why am I going to use that number? Because that is in electron volts seconds. Okay? I can't use a 6.63 number unless I change the electron volts into joules. Okay? And I end up getting a frequency of, actually, let me figure that out real quick. I get a frequency of about 7.25 times 10 to the 14th hertz. And now I can put that into C equals wavelength times frequency, and I know that's 3 times 10 to the 8th meters per second, and my frequency is 7.25 times 10 to the 14th hertz, and I end up getting that's my frequency. That is my frequency, and so I am going to end up finding my wavelength, of course, and I end up getting my wavelength is 4.14, try this on your calculator, times 10 to the negative 7th meters, which is the same as 414 nanometers. 414 nanometers. So this is going to give off a wavelength of 414 nanometers, which conveniently so is our blue light. Blue light. We can also make a transition from the n equals 2 to n equals 3. Okay? Which you can see that has a different electron volts. How many electron volts is that? That's only 2 electron volts. Guys, the math is the exact same. We have 2 electron volts. We end up getting a different, of course, we're going to use the 4.14 number, and we're going to get a different frequency when we do our math there, and maybe you want to try that with me. Our 2 electron volts gives me a frequency of 4.83 times 10 to the 14th hertz. You're going to use this instead of the 7.25 number. Guys, the math is the same. Okay, over and over and over again, the math is the same. And we end up getting a frequency, or sorry, a wavelength of, when we do the math, 6.21 times 10 to the negative 7th meters, which is 621 nanometers. So this wavelength would give off 621 nanometers. Okay, there is one last transition we can make. That is from the bottom all the way up to the 1 electron volts. And how many electron volts was that transition? You can see I went from 6 to 1, which meant that was only 5 electron volts. I divide by the 4.14 number again, and I end up getting a new value for my frequency. My frequency ends up being 1.21 times 10 to the 15th hertz. I plug that in, that equation down there, the C equals wavelength times frequency, and I end up getting a different wavelength, of course, because it's a different energy, and we end up getting 2.5 times 10 to the negative 7 meters, or 248 nanometers, okay? And that ends up giving off 248 nanometers. Guys, I know that was a lot of work there, but it's the same exact work over and over and over again. It's E equals HF. It's C equals wavelength times frequency. So make sure that you can do those equations, because in this problem, they had you do it 3 different times. Okay? Now, I'm just going to erase this real quick right there, and I'm going to come back to my problem and take a look at what C asked us for. C asked us, it said the atom is in the ground state. When an electron, you see that word electron, I'm going to circle that word electron. Why am I going to circle that word? Because now I'm using something different. It gave us a speed of that electron, and it wants to know, can it excite up to the n equals 2? Can it go all the way up to the n equals 2? So here I have, if you see, I had an electron with a velocity of 1.6 times 10, sorry, 1.3 times 10 to the 6, short-term memory loss. 1.3 times 10 to the 6 meters per second. Okay? And if you see, it was an electron. So what are we going to do? Kinetic energy equals 1/2 mv squared. I'm going to use my particle equations. 1/2, it's an electron. 9.11 times 10 to the negative 31st. I'm going to take that velocity and I'm going to square that bad boy. And I end up getting an energy of 7.7 times 10 to the negative 19th. But that's in joules, because that's the SI unit. If I divide that number by the 1.6 times 10 to the negative 19th joules for every 1 electron volt, that will kick out electron volts, and it kicks out 4.18 electron volts. Now they want to know, could I go from the ground state, the n equals 1, all the way up to the n equals 2 with 4.18 electron volts? Let's go back. From the n equals 1 to the n equals 2, it only needed 3 electron volts. Is 4.81 electron volts, is that enough energy to kick it up? The answer for that is yes. It is enough energy to jump it up the energy state. The very last question, question D, says, this is really easy, it says, another electron excites the atom up to the ground state to the n equals 2 state. And then it decays back down, emitting a photon. And we want to know the energy of the photon as it goes from the n equals 2 down to the n equals 1. What energy would that emit? That energy would emit 3 electron volts, because that is the energy from the 3 to the 6. Okay? Pretty easy, right? Let me come back, okay? And they want to know, what region is this radiation? If we come back, you can see that energy gives off 414 nanometers of wavelength. That is in the visible spectrum. That is actually blue light, okay? Now, how do I know that? You just have to kind of know that, okay? And we'll go over the electromagnetic spectrum when we get back. Guys, these are our 2 problems that I wanted to go over. We had one just straightforward and one Bohr energy. Guys, I need you to go to MrAyton.com and go to AP Physics. There are 2 Google Docs that go with this problem. Make sure you do those 2 Google Docs on atomic physics, and make sure you do that before the end of the break. Make sure you can contact me, guys. You can contact me. There's a couple people in class, like Michael Chung, you can easily contact as well. There's many people you can contact if you have any problems with these. Just make sure you do that by break, and if you need to do any extra problems to boost your grade up, make sure you go to MrAyton.com. Have a holly jolly Christmas, guys. I'll catch you on the flip side. Bye.